Welcome to all of this session. Today we'll discuss about the dynamics of the inviscid fluid. Last chapter we are talking about the motion of the fluid, and now we'll see the cause of the motion. So cause of the motion means some force is acting over it, some kind of the forces, and we'll analyze this kind of the forces. But in that case, we are considering there is a neglecting viscous force. So whether there is the other force is present, but no viscous force is present here. So this kind of the fluid is known as the inviscid fluid. It's a completely one hypothetical paradigm. And moreover, we have to see, we can assume this kind of the flow. So last example, first chapter, whenever we have seen it, the one solid plate is there and viscous effect is present over the plate, just nearby the plate. And after the boundary layer thickness, the flow is like uniform flow potential flow, where the viscous effect is very much less. So the presence of the plate will not be felt beyond the boundary layer thickness. So there the flow is considered as an inviscid flow. So where there is a very less effect of the viscosity. So this kind of the flow analysis we will do in this chapter, one by one. So I'm directly coming to the slide here. So the frame you choose here, we are going to do the laws of motion, of Newton laws of motion for the fluid, in the case of the fluid. And this dynamics analysis for the inviscid fluid. So inviscid fluid, that means the viscosity effect is neglected for the fluid. So this dynamics we will see. So whether the viscosity is not here, so only normal component of the force will be present there, like the pressure, hydrostatic force. Because the pressure is such a parameter which will be present for the case of the all cases, where the fluid is in motion, where the fluid is in rest, where the fluid is in viscous, where the fluid is in inviscid fluid, all the cases, the pressure will be present there. Hydrostatic forces. So one parallelopipe element we are choosing here, Euler's equation of the motion for inviscid fluid, we will see. Euler's equation is nothing but the Newton laws of motion. Whatever the concept we have seen, the Newton laws of motion, it's nothing but the same thing. Because Newton laws of motion is only valid for the inertial frame. Here also it is the inertial frame. So frame is a not accelerating frame. So these parallelopipe cases, we are going to choose here. Just before we'll set the coordinate first. So in this, so this is the X, this is Y, and this is Z. C coordinate, we have fixed it first. So here the pressure is acting over the element. The pressure is acting over the element. So the center point of the parallelopipe, the center point, let you take one center point here. In that center point. So center point, center of all total parallelopipe, the center point. Where the pressure we are considering that here the pressure is the P. P is the pressure at center point. Pressure at center point of parallelopiped element. Parallelopipe element. So the element, first we analyze this in the cases, the element length. So along x-axis, the length is small length, del x. Along y-axis is the del y. And along z-axis, length is del z. So what is the volume of the element? So simple. The volume of the element is a fluid element. The volume of the fluid element. We are choosing here the fluid element definitely. And the volume is the del X, del Y, del Z. And we are talking if the mass of the fluid element, similarly into density, you have to multiply with it. So mass of fluid element. So volume into density, rho, that is the mass of the fluid element. We just defined first. Now here, what are the forces acting over it? Basically the net force, whatever the net force is acting from the Newton's laws of motion, the net force, whatever acting over it, along x-axis, along y-axis, along z-axis, the total net force, that should be equal to the mass of the fluid element into acceleration of the fluid element. Mass into acceleration. That is this formula is coming from the Newton's laws of motion, because the frame is the inertial frame here. From our basic concept, we could be able to say. So at the center point, if the pressure is, so at the center point is the XY plane, the plane is XZ plane we are taking, let you take here. The plane is taking XZ. So at center, so that is the del X, and this length is, let you take, del, this part is, vertical portion is the del Z. So in such a cases, just we are two-dimensionally we are checking because it will be easy for understanding. So at the center, the pressure is a P. So if you go the left-hand side, so what is the pressure is at here? So in this zone, what is the pressure is acting over it? As the center, the pressure is that much. So in this zone, the pressure will be minus dP minus del P del X dx. Because it's the negative side. You are going here negative side. So Taylor series expansion, we are getting this. Plus some here, some additional terms will be higher order terms, but we are neglecting the higher order terms because it is a very less, because del X itself a very small quantity. So it will be another small quantity. And in that side, whatever the pressure is acting over the element. So in this zone, the pressure is acting P plus del P del X into dx plus higher order terms will be. So that is the pressure is acting over it. So force, net force is nothing but two parts of the net force. One is the surface force, another is the body force. But here surface force is only due to cause of the pressure. Here the surface force is only due to cause of the pressure. So because of the pressure, what is the force is acting over it? So let you consider in this plane we are considering. So del Z into del Y. What is the area of this part? Is the along the x-axis. So we can write it the same way in this part also. This is acting over this area. This pressure is acting this two area, hatched area. This pressure is acting. So the area is so pressure into area will gives you the force. Similarly here also the same area multiplied by. So the surface force, we can be able to write it down. So along x-axis we are considering. So net force along x-axis. So along x-axis. If you do the force, net force, what is acting? So due to the surface force, what is acting? P minus del P del X dx del Y del X. 'x'. Minus is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x' is a positive side. 'x' is a negative side. 'x P plus del P del X dx. So this is the surface force plus some body force is acting over it. So what is the body force? So let me take along x-axis, Bx is the body force per unit mass along x-axis. So Bx is the body force per unit mass along x-axis. So what is the force? So mass of the fluid element into the Bx. So we can be able to write it. Mass of the fluid element is the rho del x del y del z into Bx. So surface force plus body force. That is the net force is acting over the x-axis. So that will be equal to the mass of the element along into acceleration along x-axis. So mass of the element is the mass of the element into acceleration along x-axis. The acceleration along x-axis. So let you consider here, u is the velocity along x-axis, v is the velocity along y-axis, w is the velocity along z-axis. U, v, w. And velocity vector, in terms of the vector, that means we can be able to write it ui, vj, w. That is the velocity vector. So acceleration terms we have seen in the previous chapter, kinematics of the fluid. We can be able to write it down. So as it is along x-axis, so u component, so we can be able to write it if you remember this thing, del u del t plus u del x plus v del u del y plus w del u del z. This is the total acceleration. We can able to write it down. So if you simplify this thing, what is coming here, you see the p dy dz will be cancelled out from the both sides. This part and this part will be cancelled out. And here one thing I forget to write it, because it's the center point. If I wrongly write it, it should be minus by 2. Here it should be also by 2. Because the total length is the del x. So half of the length, because it is the at center. So half of the length should be del x by 2. Here also del x by 2. This mistake I have done it here. So it should be by 2 and this also by 2. Because it is a center. So from the center, this surface distance is the, so from the center, this distance is del x by 2. And from here also distance del x by 2. That's why here del x by 2 will come. So this term will come if you write it down in this manner. So we are just first we write this equation and we'll one by one we'll write it. So del p del x, because x by 2 it will becomes because minus del p del x and this term will be. So del x del y del z will be common from here. Here also del x del y del z is common. Here also del x del y del z is common. So it will be cancel out from the both sides. And whether there is higher order terms, for the higher order terms we can say if we convert this fluid element to 0, that means del x tends to 0, del y tends to 0, del z tends to 0. If we make it, so all higher order terms will be also eliminated. Because this kind of the force is acting over the very small element as we are taking it a differential equation. The differential equation is applicable for the very small element. So that's why. So del p del x plus, finally the equation is coming, minus del p del x plus rho bx is equal to rho du dt plus this term we can write it down. The last day we have seen also last time v dot del into u in this v dot del into u. That is the equation number 1 along x-axis. The same way equation 2 and equation 3 we can establish from the other two surfaces. That's why we are taking at the center point. Pressure is the P. So we consider here, we write it down the equation one by one. So first equation is coming minus del P del X along x-axis equation minus del P del X. Rho into Bx is equal to, so surface force, this is coming from the surface force, this is coming from the body force, into mass into acceleration. So du dt plus v dot del, because v dot del we are already previously told it, that is u del del x plus v del del y plus w del. That is the equation number 1 along x-axis. Along y-axis, the same equation will comes minus del P del y plus rho by, the body force along x-axis per unit mass, by, is equal to rho del V del T plus V. That is the second equation. Same way, along z-axis equation also coming. The body force along z-axis. It's just same manner, we are just replacing this. So the three equation we have set up here, that is along x-axis force balance, not force balance, the equation of motion, we are writing it. Because this part is the mass into acceleration. Newton's second law wise it is coming. So this is the along x-axis. His second equation is the along y-axis. And third equation is coming along z-axis. Now here, we are interested to take one line element. That means two close point we are taking. Very close point, point number, very close point. The first point, let it be coordinate is the x, y, z. And second point, x plus dx, y plus dy, and z plus z. Very small 2 point we are taking, very close point, very small distance between these 2 points. So if you join by a vector in between these 2 points, if you join by a vector, the vector is defined by dl, length element, one length vector we are taking. So dl. What is the dl? dl is nothing but we can write dx is along I, dy is along j, dz is along this line element, one line. Very close to point we are considering and we are writing it down. So in this point, let you take the point some here, small, very two close point, that's A, that's B. So pressure at A and pressure A and B point are very close, differentiable distance there. So pressure at A and pressure at B, the differential pressure between A and B will be depends on the all coordinates. So here the pressure, as the pressure is a function of x, y, and z. So the differential pressure dP we can write it down del P del X into dx plus del P del Y dy plus del P del Z. As the pressure is a function of X, Y, and Z. Along X-axis pressure is changing, along Y-axis pressure is changing, along Z-axis pressure is changing. So the pressure changing between the two close points, that is the equation. So in that equation, del P del X value, you can put it here from equation number 1. So del P del X value, you can put from equation number 1. Del P del Y value, you can put equation number 2. And del P del Z value, equation number 3. This equation, from this equation, we can put the values. And after putting the values, we can write this equation in this manner. So we are rewriting this thing after putting from this. So dp, so del P del X, you see here del P del X, what is the value? So del P del X value, we have to choose from here. So del P del X value is nothing but rho bx minus rho into this term. So rho bx minus rho into del u del t plus p dot del into u. From this equation, you see. That is so this total into, this is the second bracket. This total into dx. The first term is like that. What would be the second term? Same way, rho by minus rho del v del t plus p dot del v into dy. We're just putting here del P del X, del P del Y, and del P del Z here. And the same way, rho bz minus if you remember here, first assumption, whenever we are going to do, the first assumption we are taking, that is the inviscid fluid. First assumption was the inviscid fluid. Then only no viscous term came in the equation. In the surface force equation, only due to the pressure. No viscous term came. That is the first assumption. First assumption. Now you see here, the term, if you rearrange this part, this three part you can take a single way. So we can be able to write it. Rho bx dx plus by dy plus bz dz. We are going to rearrange this case. Minus rho, this part we are now, this part we are taking same way. So del u del t dx plus del v del t dy plus del w del t dz. And the third part, minus rho v dot del, that is a common for all, u dx plus b dy plus w. Three terms will come here. There is the first term, second term, third term. So dp equation, in the dp equation, after putting these values, three terms having come here. So this is the term 1. We can write it down. This is the term 1. Second part, is the term 2, and third part is term 3. So what is the term 1? Whenever we are going to discuss term 1, we take one assumption. The second assumption is that gravity is the only body force. Second assumption, we are taking it here that the gravity is the only body force. So gravity is only body force. So gravity is always acting z direction. You see here the gravity force here, because it was x, it was y, it was z. Gravity is acting always negative z direction, g. So as it is acting the negative z direction, so only bz is minus g, because it is a negative part. And bx is equal to 0, and by is equal to 0. No body force along x-axis, no body force along y-axis. That is our assumption. So the term 1 can be reduced to, minus rho g dz. Term 1 can be reduced to minus rho g dz, just putting the bz values. About the term 2 we are discussing here. Just if we discuss about the term 2, you see the equation we have written that rho into del u del t dx plus del v del t dy plus del w del t. So it can be written as rho del v vector dt into dl. Because dl is, if you take it, this dl is a dot product. It's a dot product. dl is nothing but dxi plus dyj plus dzk. And this part is del u del ti plus del v del t j plus del w del t. If you do the dot product, so it will come del u del t into dx, del v del t into dy, del w del t into dz. So the term 2 also can be reduced to in this manner. So term 1 and term 2, we can reduce it easily. Now about the term 3 we are going to discuss. So term 3, I am rewriting this term 3 here first. So the term 3 is, what is here? Rho v dot del u dx plus v dy plus w dz. U dx plus v dy plus. So this part, u dx plus v dy plus w dz, we can write it down v dot dl. This can be replaced because v is ui plus vj plus wk, and dl is dxi plus dyj plus dzk. So it can be easily write it down in this. So we can rewrite this equation. Rho v dot l v dot d. Okay. Rewrite this part. But here, this part. Okay. Now, after getting this thing, we are taking one vector identity here. So vector identity is the most important thing. Some vector identity is there. Whenever you are seeing the vector calculus in engineering mathematics, you will see this is one vector identity. This part is equal to, we can write it down, half of del v dot v minus v cross del cross v. That is coming from the vector identity. You can prove it by taking the x, y, z coordinate along velocity vector u, v, and w. If you put it and you right hand side, left hand side, you can take it. You can check by your own. But there is the vector identity. We have to remember this part. So this part can be replaced by this one. This part can be replaced by this one. So in this part, we can replace from vector identity. So what is that? It is coming rho half del operator of v dot v into dl, because dl is multiply with the both term same way, minus v cross del cross v, that will be multiplied with dl. This part will be multiplied with dl. So this is the ultimately third part can be reduced. So again, we rewrite the pressure difference. So dP equation after term 1, term 2, and term 3, we are getting all this thing. Term 1 is getting minus rho g dz is equal to minus rho g dz. Term 2, we are getting it. Term to this term, rho del v del t dot dl. Rho del v del t dot dl. Term 1, term 2, and now the term 3. Half del v dot v dot dl minus is a v cross del cross v. That means that it is a curl of v. Curl of velocity vector, it can known as the vorticity also. We know this is the nothing but the vorticity. We'll see that is the part. That's the ultimately equation is given. This part, the first part. So first part means this can be reduced further. Half rho del v dot v dot dl. This can be reduced further because v dot v. What is the v dot v? V dot v means u square plus v square plus w square. Because ui plus vj plus wj, this part is the ui vj plus wk, same way this one. So it will come in this way. So that is nothing but the v square. This is nothing but the magnitude of the v square. So this is the part. So half rho del v square dot dl. V square dot dl. Now you see here one more interesting part. After doing this operation is the easy part. Now this part, does it mean? This part is meaning that half is common, half and rho is the common. Del of v square is nothing but I of d dx v square plus j of d dy v square plus k of d dz v square. That is the del v square meaning. Is the meaning of del v square. And dl is I of dx plus j of dy plus k of dz. That is the dl. If you do the dot product of it, so it will comes in this manner. Half rho del x v square into dx plus del y v square into dy plus del z v square into dz. What does it mean? It means half rho dv square. Half rho dv square. Simply, we can write it down. So del x v square dx plus del y v square dy plus del z v square dz. That is nothing but dv square. That can be reduced. So ultimately, what is the equation is coming? Again, we rewrite this equation. So just I rub this part and again rewrite this thing. So dp is coming. First term is coming here minus rho g dz. Second term is coming here. Second term plus rho del v del t dl. And third term is coming here minus half rho d of v square. Okay. This part is a negative part. This part is the negative part also. It will comes in negative. In here it is also negative. Sorry. It's not positive. This is a negative also. Plus rho v cross del cross v dot dl. This is the part here. So the dp plus half rho dv square plus rho g dz plus rho del v del t dl is equal to rho v cross. So curl of velocity vector is known as the vorticity vector. Curl of the velocity vector is known as the vorticity vector. Sorry. So vorticity vector, we can write it down, vorticity vector in terms of also. So vorticity vector dot dl. This is known as the Euler's equation of motion. This is known as the Euler's equation. This is a general equation in terms of the vector. Equation of motion. Euler's equation. In the Euler's equation, so what are the assumptions we have taken for the equation? So if you recall the first assumption, if you recall the first assumptions, is a inviscid flow. Inviscid fluid, sorry. So inviscid fluid, first assumption. Second assumption, gravity is only body force. These two we have taken till now. Till now, these two assumptions we have taken. Now, further assumption we are taking it. That is, if it is a steady flow. Third is if you are taking it's a steady flow. So steady flow means this part will become 0 because del V del T will become 0. So this part will become 0. So as it is steady part, so this part becomes 0. Okay. Next assumption, the fourth one, is the most important assumption. Fourth one assumption is, what is the condition for this term becomes 0? What is the condition? To try to understand it is a very minutely. Condition for V cross omega dot dl is equal to 0. What is the condition for itself? First condition is along a streamline. If it is along a streamline, what does it mean by the streamline? Streamline means from any point, if you draw a tangent, it will gives you the velocity, instantaneous velocity. That means V vector and dl vector are in same direction, So V vector and dl vector are in same direction. So along a streamline, if V cross curl of V dot dl will become 0. How? Because this V and dl are in same direction. Let you take, for example, just for the sake of, let the V is along I axis. Let you take the V is along I. And dl also the same will be I. So V and dl is the same. This we just here one roughly. So the condition we are telling it, the condition for V cross curl of velocity vector or vorticity dot dl for 0. What is the condition? We are searching for the conditions. So first condition we are taking along a streamline. So V vector and dl vector both let you take along I direction. Both let you take I direction. So V is I. So curl of velocity vector, it will be perpendicular to I, whether maybe J or maybe K. Curl of velocity vector. Because curl of any vector will be perpendicular to the same vector. Now, the V cross del cross V, this direction, so if V is along I and this is along J, so this direction will become along K, perpendicular to I and J. If it is become K, so then it will be J. So perpendicular to it. Because I cross J will comes K, I cross K will comes minus. This one. Minus. If V is I, so del cross V J, so I cross J if it will come nearly K vector. If I cross K, it will comes minus J. So ultimately this part direction is either K or minus J. So whenever V cross del cross V, so this vector either K or minus J. Dot dl, dl is the I. So I is perpendicular to K and as well as J. So dot product will always become 0. So along the streamline, if you are considering the 2 point, if the 2 point is along a streamline, any 2 point along a streamline. So this part will be always 0. This part will be always 0. That is the first condition. What would be the second condition? The second condition is the curl of velocity vector itself 0. Is itself a null vector. So curl of velocity vector itself 0 means irrotational flow. We have already discussed the previous chapter. It means that irrotational flow. So the two conditions, either it may be along the streamline, or it may be the irrotational flow. Both cases. So condition here, first condition along a streamline, and the second condition, I'm writing it down. So condition for this part becomes 0. Will be irrotational flow. If the flow is irrotational, so these are the assumptions. Inviscid flow, gravity is the only body force, steady flow. Condition for this second, the year was fourth one is the either it should be along streamline or irrotational flow. So if we take this all assumption, if we take, so this part will become 0 and this part will become 0. This two part will become 0. And what would be the remaining part? So remaining part, we are writing it down here. The remaining part will be del P plus half rho dV square plus rho G dz is equal to 0. Now it's time to take another assumption. That is a constant density flow. Density is constant density flow. There's a fifth one we are taking. So rho is a constant here. It does not depend on the X, Y, Z or something else. Next, in between 2 points, point 1 and point 2, if we do the integration, if we perform the integration of this equation is the Euler's equation of motion. With such assumption, number of 5 assumptions we have written. So 1 to 2 plus half rho. Rho is a constant, half is also constant. It will be coming out of integration. Half rho dV square plus rho G, again constant both, 1, 2, is equal to 0. So it will come P2 minus P1 plus half rho P2 square minus P1 square plus rho G Z2 minus Z1 is equal to 0. So P1 plus half rho P1 square plus rho G Z1 is equal to P2 plus half rho V2 square plus rho G Z2. If you divide it by rho G, so P1 plus rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus V2 square by 2G plus Z2. This is the most popular equation known as the Bernoullis equation. In the fluid mechanics, we are always using this equation Bernoullis. But you keep it in your mind, the following assumption should be satisfied, then you can be able to apply the Bernoullis equation. What are the following assumption? Again, we recap in the next lecture. The same thing, we are recapping the next lecture. So this way, we have to prove the Bernoullis equation.